Chapter 6.4. This is a short section. First thing that I want to do is review population parameters. Now remember, population is every item, every person. The numerical description from a population is called a parameter. And what we have been discussing already this semester is a population parameter mean is known as mu. The variance is sigma squared, and the standard deviation is sigma. And then the numerical descriptive measurement for a sample is known as a statistic. So, and remember, a sample is finding the value from a portion of the population. So the sample statistic mean is known as x bar, variance s squared, standard deviation s. So I just want to go over those again. Now, what this reads is often we do not have access to all the measurements from the entire population, so that's why we use a sample. Then what we'll do is take that sample statistic and make inferences or infer information to the population. Now, to complete this semester, these are some of the discussions we will have. One is on estimation, which is going to be in Chapter 7. Testing, which is going to be in Chapter 8, and then to complete the semester, we'll talk about regression, which is in Chapter 9. Now, one other thing that we need to have a discussion on, because that's what we're going to be doing in 6.5, is a discussion on a sampling distribution. Okay, so I've given some bullets here, but I always think it's better if I can just show this to you. So, we have been talking about probability distributions. So let's say that we have a population of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 x values. These are x values, individual values that go to an individual person or an individual item. With your x values, let me try to pull this out a little bit. I want to get more in here. If it's the population, then the mean is known as mu, the standard deviation is sigma, and then what we did in 6.3 was we took those x values, we converted them to their z value, and then found their probability. Well, sometimes we work with what's called a sampling distribution instead of a probability distribution, so I want to show you what a sampling distribution is. Sampling distribution means a distribution of values that originated from a sample. So let's say that we take our population in the probability distribution and we are going to group them in values of 4 and find their mean. So let's say I took these 4 values, which would be a sample of this population, added them all up and divided by 4, that would yield a value that we would call x bar. And then say we did the same thing for these 4, so that would give us another value, add them all up and divide by however many there are, that is a mean or x bar. And then we would take the last 4 and calculate their mean, which is x bar. So then if we distributed the 4 values, so say this time we grouped these 4 together and calculated another x bar, and then we grouped, say, these 4 together and created another x bar, and then these 4 together and created another x bar, and say we just kept doing this until we exhausted all the different groupings of 4, but now we have a group of values that are x bar values. These do not refer back to one individual item or person. Each of these numbers refers back to an average of 4 people or 4 items. This is what we call a sampling distribution because these numbers came from a sample. So now instead of having x values, we have x bar values. Now, what we'll get into in 6.5 is we'll actually apply this information, but the mean or the average of the x bars is equivalent to mu. The standard deviation of the x bars is equivalent to the standard deviation divided by the square root of n. And then notice then the z value now changes because we have x bar minus mu divided by sigma divided by the square root of n. Now, when we get into chapter 6.5, here's the key is knowing when to use this z value when you have one item, one person, as opposed to using this z calculation, and this is when you have an average of multiple people or multiple items. So that's kind of an introduction for 6.5, but it is talked about in 6.4.